So far, we've talked about how plane waves propagate through dielectrics. So let's not leave the conductors out in the cold and take a quick look at how our solutions to Maxwell's equations also describe propagation in conductors. Conductors are described by their conductivity, sigma, which it relates, as we previously discussed, relates to the imaginary component of permittivity. And in general, if it's a good conductor, that means that sigma is large. So if we assume that sigma is large, then let's go back to our general expression of Jk and see what that does. So remember, we started looking into lossy media by saying that Jk, instead of k being a real number, we say Jk can be a complex number. So alpha plus j beta, where in a lossless situation, alpha is going to be equal to 0. And we had also previously discussed about how that's equal to j omega square root mu epsilon real part over square root times square root 1 minus j sigma over omega epsilon. So if we were to rewrite this in terms of sigma instead of epsilon double prime. And if sigma is going to be large, that means that we can disregard this portion, since this term is going to be much larger than 1, since sigma is going to be a lot larger than epsilon prime. And so you're left with j omega square root mu epsilon prime square root j sigma omega epsilon prime. And that is going to give you just a single complex number, j, of 2 pi f mu sigma, 2 pi f mu sigma of 1 plus j, which means that, so remember the real part is alpha, the imaginary part is j, and now you have the real part and the imaginary part being equal, right? So if sigma is large, then we end up with expression that alpha is approximately equal to beta, and they're both approximately equal to 2 pi f, which is our omega there, of mu sigma. So what you end up finding is that when sigma is large, alpha and beta are approximately equal, and that quantity is going to be the square root of 2 pi f mu sigma. And so remember, the field decays as a function, as a shape of e to the minus alpha z, right? So it has a e to the minus 1 decay. So what we often define is the skin depth, so the location where it decays to e to the minus 1 of the original signal. So decay to e to the minus 1 by a factor of e to the minus 1. That is what we call the skin depth, which, so again, if this is the distance for it to decay to e to the minus 1, that means that delta is going to be equal to 1 over alpha, which is going to be equal to 1 over the square root of pi f mu sigma. So we've introduced the concept of the skin depth, which is basically just saying if I have a conductor here, which is very grumpy, doesn't really like any waves to go in, and a wave tries to go inside, it's going to decay. And the amount, if you say I only care up to the point where it decays by a factor of minus 1 over e to the minus 1, then that is going to be my skin depth, delta. So for as a rough approximation, if you say decaying by e to the minus 1 is the majority of the signal, the skin depth is the total amount of area where the atoms inside actually interact with and feel the electromagnetic wave. And so if you were an atom sitting over here within the skin depth, you would feel the wave coming in and it would be decaying. But if you were this other atom sitting right here, you wouldn't even feel the wave because the conductivity ends up getting rid of most of the wave. So you'd just be here taking a nap. You wouldn't even know that the wave is there. So the skin depth is kind of, as it sounds, it's a measure for the amount of penetration that the propagating wave would have if it tried to enter a conductor. So if we applied the same kind of approximation to eta, we'll find that eta is going to be equal to the square root of j omega mu over sigma plus j omega epsilon prime. And again, we're assuming sigma is much greater than epsilon prime. If we do some other approximations, you'll find that for a good conductor, you can approximate eta as 1 plus j over sigma delta. And then finally, if you also say that h is going to be equal to E divided by eta, and you have your expression of E that decays as a function of alpha or as a function of 1 over delta, you will also find that for a good conductor, the time average power density as you propagate is going to be 1/4 of sigma delta Ex squared e to the minus 2z over delta. So this is a simplified expression. Again, the exact expressions that we had in previous lectures still apply here, but this is an approximation if you were given a delta and a sigma and you were told that it was a good conductor. Now, if we wanted to calculate the power dissipation, or effectively the ohmic dissipation that occurs, you can integrate this across a surface area, right? So let's just say you're talking about an A times B rectangular cross section. Then you can say that the power loss in a rectangular cross section of A and B could be 1/4 sigma delta AB Ex squared, or if you had it in terms of current density, remember the current density relates to the E field through the sigma term. You will end up with the power dissipation is going to be equal to 1 over 4 sigma delta AB Jx squared. Now, one thing to keep in mind, that the impact of the skin depth also means that the behavior of the current in a conductor actually ends up depending on the wavelength. So let's take a look at an example of that. So let's end by looking at a cylindrical conductor and a skin depth delta. So if this is our conductor here, and we have a radius A, this is our cross section, so the conductor runs this way, and you have your wave running through it. If delta is if delta is a lot greater than A, that means that it's able to penetrate the whole thing, right? So that means that your wave is penetrating the whole thing, and you have that kind of ohmic interaction throughout the entire cross section. So then your resistance would be L over sigma A, right? Or L over sigma pi A squared, right? The cross section area. So this is kind of what you would expect. But separately, if the skin depth is much less than A, for example, if you see this is frequency dependent, if the frequency is really, really high so that the skin depth is a lot shorter than this, then in essence, instead of having the field going all the way across, you end up only having current along this outer skin, right? That's the name skin depth. So as the wave goes through, you instead of having current ohmic dissipation across the whole thing, you only have ohmic dissipation across this outer ring, because outside of that, the wave doesn't really penetrate, right? So in this case, your resistance is still L over sigma A, but the cross-sectional area is no longer the whole pi A squared, right? The cross-sectional area is the size of this ring, right? So instead, it's going to be equal to the circumference times, if we were to chop this up and turn it into a rectangle, one side of the rectangle would be the circumference, and the other side of the rectangle would be the skin depth, right? So it would be instead 2 pi A delta instead of pi A squared. So this is a specific example of when the skin depth would matter when you're trying to calculate the ohmic dissipation of a conductor.